In this video, we are going to discuss the arrangements of a given set of objects when some of them are identical, that is when the objects are not all distinct. Suppose we have 5 objects among which 3 are identical, say A, B, X, X, X. Now since we are familiar with the permutations of distinct things, so let us mark these identical things with subscripts 1, 2 and 3 so that we can identify them distinctly. And now as we have 5 distinct things, so we can arrange them in 5 factorial, that is 120 ways. Now observe the first and third entry. In these entries, A and B are at the same place while x1, x2 and x3 have arranged among themselves, which we can see only because of their subscripts. If we remove the subscripts, then we will not be able to tell the difference as they look the same. Let us group these arrangements together, and total number of such arrangements where A and B are fixed while x1, x2 and x3 arrange among themselves is 3 factorial. Again observe these entries. They too have A and B fixed at the same place while x1, x2 and x3 interchange among themselves. As before, let us group them together. And since in these arrangements also only x1, x2 and x3 interchange among themselves, so the number of such arrangements is 3 factorial. Similarly, number of arrangements of this type where A and B are at the 4th and 3rd position while x1, x2 and x3 interchange is also 3 factorial. So in this way, we can classify the total 5 factorial arrangements in groups of 3 factorial, where each group gives a unique arrangement of A, B, X, X and X. And the number of such arrangements is 5 factorial by 3 factorial. So 5 things, of which 3 are identical, can be arranged in 5 factorial by 3 factorial ways. We would have got similar result if there were 7 things, of which 4 were identical. The number of arrangements then would have been 7 factorial by 4 factorial. We can use this result to answer questions like, in how many ways can we arrange the letters of the word Twitter? Since the word Twitter has 7 letters, of which 3 are identical, so number of permutations is 7 factorial by 3 factorial. What if there are more varieties of identical things, like if there are 6 objects, out of which 3 are identical of one kind and 2 of other kind? Since there are 2 sets of identical things and we will not be dealing with both of these at a time, so let us place subscripts on y to make the 2 y's distinct. And by doing so, we have reduced it to the previous type. Now we have 6 objects of which only 3 are identical, which can be arranged in 6 factorial by 3 factorial ways. Now notice the first and fifth arrangements. In these arrangements, only y1 and y2 have interchanged among themselves. And so, without subscripts, both these arrangements look identical and will appear as A, X, 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 Y, Y. Since y1 and y2 can interchange in 2 factorial ways, so there are only 2 of such type. Similarly, the third and fifth arrangements are also identical without subscripts and will be counted as 1. In this way, since we are counting 1 for 2, so the total number of such arrangements will be 6 factorial by 2 factorial times 3 factorial. So 6 objects, of which 3 are identical of one kind and 2 of other kind, can be arranged in 6 factorial by 3 factorial times 2 factorial ways. We can generalize this and apply it to a collection with more variety of identical things. For example, the word assassination has 13 alphabets, of which there are 3 A's, 4 S, 2 I's and 2 N's. So the letters of the word assassination can be permuted in 13 factorial by 3 factorial, 4 factorial, 2 factorial and 2 factorial ways. In general, n given things, of which p are alike of one kind, q of other kind r of another kind, and so on can be arranged in n factorial divided by the factorial of frequency of repeated objects. Let us go through some examples based on the above result. The first part of the question is to find the number of different words that can be formed by arranging the letters of the word constitution. Some example words are as follows. And we want to find the total number of such words. The word constitution has 12 alphabets, of which there are 3 T's, 2 O's, 2 N's, and 2 I's. So these alphabets can be arranged to form different words in 12 factorial by 3 factorial times 2 factorial cube ways. For the second part of the question, we need to keep the vowels together. Recall that to keep some particular things together in an arrangement, we bind them and treat them like one single object. In this case, we want to keep the vowels together, so we bind them and count them as 1. Now 8 things, of which 3 T's are identical and 2 N's are identical, can be arranged in a total of 8 factorial by 3 factorial times 2 factorial ways. Further, the 5 vowels, of which 2 O's are identical and 2 I's are identical, can arrange among themselves in 5 factorial by 2 factorial times 2 factorial ways. So in this many number of arrangements, the vowel will be appearing together. In the third part, none of the vowels must be next to each other. This is a case of strict separation, so we arrange the separators first. Since the vowels are to be separated, so the separators in this case are the consonants. 7 consonants, of which 3 T's are identical and 2 N's are identical, can be arranged in 7 factorial by 3 factorial times 2 factorial ways. In between these 7 consonants, there are 8 places, on which 5 vowels can be arranged in 8p5 ways. But since these vowels have 2 identical I's and 2 identical O's, so we divide by 2 factorial times 2 factorial. So there are this many arrangements in which no 2 vowels appear together. Next example is, how many 7-digit numbers can be formed using all the digits 0, 1, 2, 2, 2, 3, 3? The given 7 digits have 3 identical 2's and 2 identical 3's. So these digits can be arranged to form new numbers in 7 factorial by 3 factorial times 2 factorial ways. But many of these arrangements have 0 at the first place, making them a 6-digit number. So we need to exclude them from the total count. To find the number of such numbers that start with 0, we fix 0 at the first place, and then the other digits can arrange in 6 factorial by 3 factorial times 2 factorial ways. So the required number of 7-digit numbers are total arrangements minus those that start with 0. Next problem is, in how many ways can we get exactly 3 heads when 7 coins are tossed? We have 7 coins and each can show a face in 2 ways, head or tail. We need to arrange these 7 coins in such a way that exactly 3 of them show head while others show tail. For example, right now we have these 3 coins showing head and the other 4 showing tail. Or we can have these 3 coins show head while the other 4 coins show tail. So in a way we are arranging 7 things, of which there are 3 identical heads and 4 identical tails. And total number of such arrangements is 7 factorial by 3 factorial times 4 factorial, which calculates to 35. So 7 coins can show exactly 3 heads in 35 different ways. For the next example, consider this 5 into 4 grid with this bottom left vertex as A and top right vertex as B. The question is, in how many different ways can we go from point A to point B using only an up step and or a right step? One possibility is to go up, then 2 times right, then 2 times up, then right, again 2 times up, and then right. Another way is to go 2 times right, then 3 times up, then again 2 times right, then 2 times up. We want to find the total number of such possible ways to go from point A to point B. Note that point B is 5 steps above point A, so we always have to take exactly 5 up steps in any order to reach B. We can verify this in our examples. There are 5 views in each of them. Also, B is 4 steps on the right of A, so we have to take exactly 4 right steps in any order to reach B. This means as long as we take 5 up steps and 4 right steps in any order, we can always reach B from A. So these are all different arrangements of 5 U's and 4 R's, and total number of such arrangements is 9 factorial by 5 factorial times 4 factorial. So in this many ways we can go from point A to point B using an up and or right step. There is yet another case where we will be using the same result which we use for arrangement of identical things. These can be called ordering problems. An example problem can be as follows. Suppose on a particular school day there are 6 periods. Also there are 6 subjects, namely physics, chemistry, maths, history, English and geography. Then in how many ways can we assign periods to these subjects so that physics is always before chemistry and chemistry is always before maths? An example allotment can be this, where physics is before chemistry and chemistry is before math, or this. Note that the subjects physics, chemistry and math need not be next to each other. They may not be adjacent, but they have to maintain the order in which physics is before chemistry and chemistry is before math. To find the total number of such arrangements, what we do is, we replace those things which are to be in a given order, that is physics, chemistry and math, with blanks. And then we freely arrange them. Since we are arranging 6 things, of which 3 blanks are identical, so the total number of such arrangements is 6 factorial by 3 factorial. Now if we take any one of these routines, say the 4th one, then we have English and history on the 1st and 2nd period, and even though we have a blank on the 3rd period, still there is no confusion about the subject. It cannot be math or chemistry, it has to be physics. Similarly, the next blank of 5th period has to be chemistry, and the last blank has to be math. In fact, each of these routines, even with the blanks, are pretty clear. The blanks in each one of them can be filled in just one way. First physics, then chemistry, and then math. So there are this many possible ways in which we can have a routine where the subjects physics, chemistry and math follow a specific order. We can think like this whenever we come across an ordering problem, or we can generalize the process into a rule as, if in an arrangement some particular things are to be in a given order, then we treat those things as identical. For example, in how many ways can we arrange the letters of the word animation so that the vowels are in alphabetical order? So we have the word animation, which has vowels A, I, O, and consonants N, M, T, N. Alphabetical order of the vowels is A, I, O, so they must appear in this order. For example, in this arrangement, we have all vowels ordered alphabetically. I encourage you to go through the entire thought process yourself and solve this problem just like the previous one. But now I will be using the rule that these things which are to be in some given order must be considered identical. In this case, since the vowels have to be in alphabetical order, so let us consider them identical by replacing them with identical blanks. Now we have 9 things to arrange, of which 5 blanks are identical and 2 n's are identical. So the total number of required arrangements is 9 factorial by 5 factorial times 2 factorial. That is all for this video. These are some questions for practice. Some of these questions are a bit difficult, but still try your best and go through all of them. In the next video, I will be solving some of these questions and also some other problems involving everything that we covered so far. In case of any doubt, you can reach me at this address.